One was about grammatical use of the word shielding, I guess. So you can say something is like best at shielding, or you could say least shielded. These two are equivalent statements. So I would imagine, I don't know, I guess some warrior or something with a shield. If they're best at shielding, meaning they're best at protecting, or in terms of the core electrons, they're best at covering up the nucleus so that the valence electrons can't see the protons. Let's go back to this picture here. So something that's really good at shielding, an example would be the core electrons. They're really good at shielding, and at the same time, nobody's shielding them, so they're the least shielded. Nobody's blocking the nucleus from the core electrons. So you could either grammatically say the core electrons are the best at shielding in compared to the valence, or you could say they're the least shielded, meaning they're not blocked by anyone. So both would be grammatically equivalent statements about shielding. Is that okay? Okay, somebody else. Yes. Well, yours was a test question, right? Okay, give us the exam. Okay, I'm flipping over to winter 2014. What number? 18. This is page 78 of this quarter's reader. Are you talking about this one here? Electron initially is n equals 8. Okay. So that one, for most people, is more of a math issue compared to anything else. Okay, so let me set it up. Electron is initially at 8. Okay, of a Bohr atom or Bohr hydrogen atom. And then we have a photon that's emitted at a wavelength equal to 7.51 micrometers, or that's 7.51 times 10 to the minus 6 meters. Okay? That's what a micrometer is. And it's emitted. Okay, so yeah, n final is larger or smaller than n initial if it's emitted. Is the electron going up in orbit or down? Down. So the n final has to be smaller. Is that okay? Whatever it is, it has to be a smaller number. So it's anywhere between 1 and 7 if it's going down. It went down to the 7th or 6th or whatever. We're cool with that? Okay? So let's write down the formula now. Change in energy equals hc over lambda equals Rydberg constant 1 over n initial squared minus 1 over n final squared. Okay? All right. Is energy a positive or negative number? If it's emitted. Negative. So when you do this calculation, if you have both 8, which 8 goes right here, and then whatever this number is, you should get a negative number out of that. Okay? So what I would do is I would say, okay, let's do this left-hand side first, because I have all the variables for that one. Basically, you want to know what n final is the question. Okay? So you would say, well, change in energy is let's write it out, 6.626 times 10 to the minus 34 joule seconds. That's a given on the back of the exam. C is the speed of light, 2.9979 times 10 to the 8th meters per second, given on the exam. Lambda is given, it's 7.51 times 10 to the minus 6 meters. So you're going to find the energy. Cool? Find that numerically. You're going to set it equal to this, but you're going to make it negative. Now we're going in reverse. Usually we take the absolute value and then find the wavelength. Now because we're going backwards, I need to make sure that whatever value I put in here, I make it negative. Otherwise it's not going to work right. If you don't make it negative, you're going to get a larger end final number, meaning you're assuming it was absorbed. And so you would just then algebraically solve for end final. So try that, see if that works out for you. So the biggest problem that most students had when they solved this is they didn't put the negative here. Because they didn't realize, oh, it's omitted, so I need a negative there. Yeah. Yeah, it says that word in the question. Omitted, right here. All right, who was next? I said you were third. Yes. Do you have the page? 52? 54. Page 54 in the practice exam reader. What number again? Whoa, yeah, you're way off. Okay, winter, what year? 2015. 64. What number again? What number? 17. For this one? Is this what you're talking about? No. Wait, fall. No, you didn't say fall. Winter. 70. Okay? Try that one. This one. Okay, nice. Page 70. This is winter 2015, number 17. Fluorine. Well, fluorine is 1s2, 2s2, 2p5 on the periodic table. So 1s2, 2s2, 2p1, 2, 3, 4, 5. This is fluorine, right? Yeah. Right. The question was, what does the noble gas have to do? Nothing. It could have also said ground state. It means what we're saying is the lowest energy state. Yeah. Meaning write it normally. Yeah. Okay, good. Next. Yes? Okay, page 60. Hold up. Let me find that. I'm talking about this one right here. Okay, this is page 60, winter 2016. I gotta zoom out a little bit here. Okay, let's see what we have. We have a gas. Looks like there's only one gas. So it's a 10-gram sample. It has a volume, so we got a mass. We got a volume of 5.25 liters. See what else we have. I know it's going to go off screen a little bit. The temperature is 25 degrees C. And we've got a pressure. The pressure is given at 762 millimeters of mercury. Okay. If 2.5 grams of the same gas is added to this, okay, so we got this. Get another color now. I'm adding in 2.5 grams of the same gas to this constant. Okay, this is constant. That doesn't change. The volume of the container is pretty rigid, it looks. The temperature goes up to 62 degrees C. What's the new gas pressure? Okay? So, I'm seeing things change. So I'm thinking of one of the gas laws like Boyle's, Charles, etc. I prefer the combined gas law, so I'm going to use that one. All right? So let's try it. R is PV over NT. P1V1 over N1T1. That's state 1. Then P2V2 over N2T2. Okay? Now notice the volume stays constant. So we don't need that action. Okay? I want to know really P2. Because I want to know the final. So I'm looking for that. I know P1. Let me squeeze that in there somewhere. That's 762. That's P1. I know T1. That's 25. And I know T2, that's 62. Let's wait for N for just a second. P1, do I need to change the units? I could change the units, but I don't have to. Why not? Because I'm using a gas law question. In Boyle's, Charles, combined gas law, all those. Because I have an initial and a final state, I'm just going to get P2 in the same units as P1. Is that cool? Okay, temperature. Do I need to change the units? That one, yes, because it has to be in kelvins. Has to be in kelvins. Okay? Yeah. If you convert the pressure, you wouldn't be wrong, but let me walk over. Let's see, that was number 6. All the answers are given in millimeters of mercury. So if you convert this to atmospheres, you get atmospheres here, you have to convert back again to millimeters of mercury. Okay, so I'm going to change the temperatures to Kelvin. Is that okay? All right, now, this is the same gas, so can I just put the mass right in there? For example, 10, and then 10 plus 2.5, or 12.5. Because this is moles. So can I just put the mass right in there? I can in this case because it's the same molar mass. So notice they don't give you the molar mass. That's because you don't need it. It's the same for both. If they said it was 15 grams per mole, it wouldn't matter because it's the same for both. Usually you would just change it. But in this case, it's the same, so it would cancel out on both sides, and that's why the question didn't give it. So you're just going to put the masses in here of what was the initial one? 10. And then the final would be the sum, 12.5. Is that okay? Next. Who's next? Oh, we're done. Oh. Page 109 is what I'm flipping over to right now. What number? 10. This one right here? Okay. So, I'm going to move this out of the way. Don't need that action. I just want to try to go through these fast so I can get as many people as possible. I have 888 centimeters. By the way, it's page 109, winter 10, number 10. Centimeters cubed. That's a volume. Just note that. We got a volume. It's collected. Oh, I see the key word. Over water. That makes me think this is most likely a Dalton's law problem. Let's see what else we got. Temperature. The total pressure. Let's see. What is the partial pressure of the gas? Is the question. Okay? So, this is definitely a Dalton's over water sort of problem. Remember what I said. When it's collected over water, the P total would be the gas plus the pressure given by the water. So let's see what we got here. We want this. That's what we want. P total, right there. Okay, that's given. The partial pressure of the water, where the heck do I find that? In that dumb table. So let's find it. Right here, it's given on the test. It was 25 degrees C, is that right? So 23.76 but in millimeters of mercury. So this is from a table. Zoom out again. 23.76 millimeters of mercury. The question, oh shoot, what page was that on again? 109? The answer wants the units in millimeters of mercury. So I need to convert this to millimeters of mercury, and then I just merely subtract. Is that okay? So I don't need either of these numbers. I don't need that number specifically. It's just a volume, whatever, unnecessary. Okay, you're good? How do you go to kilopascals? Pascals? Well, you go 55.8 kilopascals. There's 1 kilopascal. in 1,000 pascals. And then you use the back of the exam. Let's see, 760 millimeters of mercury for every 101,325 pascals. It's on the back of the exam. So you don't even need to memorize it, so hopefully that didn't scare you. Just written right here. 760 millimeters of mercury is equal to 101,325 pascals. All right, next. Yes? 76. Are we talking about this one here? Okay. 76, number 6, winter 2014. 76, number 6, winter 2014. So there's 3 volumes of O2. There's 1 volume of CH4 are in a sealed container. Meaning, if this was 3 liters, this would be 1 liter. Or if this is 3 milliliters, that would be 1 milliliter. It's a 3-to-1 ratio. Okay. The temperature and pressure, okay, temperature is 120 degrees C. Pressure is 600 kPa. What is the pressure in the same container after the explosion of the mixture and after it was cooled to the initial temperature? Okay, so, oh shoot, my timer's going off. Hold up. Make sure life is okay. Yes, I'm fine. Okay, so, gotta check your timer when it goes off. Okay, when it says the word explosion, what does it mean in terms of what type of reaction is now occurring? A combustion. So whenever you see an organic with O2, it's a combustion. Let's write out that reaction. CH4 plus O2 goes to CO2 plus water. So if there's a reaction, always write it out. In this case, there is a reaction. Let's balance it. 1 here, 1 here, 2 waters, and how many oxygens? What number do I put here? 2, I think. Okay? All right. So, let's do it this way. Start and end. Okay? In the start, we have 1 of these, 3 of those, 0 of those, and 0 of those. That's the initial, before the reaction occurs. Okay? Then what happens, in the end, 1 of these reacts with 2 of these. Is that okay? 1-to-2 ratio. So there's going to be 0 of these and 1 of those left over at the end. And then we're going to make 1 of these and 2 of those. Is that okay? Meaning I had 1 extra oxygen that was unused. Yeah. If I started with 1 and 3, well, 1 reacts with 2. So the 1's gone, and 2 of those are gone. And it forms 1 and 2. Is that all right? Okay. So, now I forgot what I was doing. Let's see. What is the pressure after? Okay, so we have the pressure before. We want the pressure after. Okay? So, because things are changing, I'm thinking the combined gas law. I forgot who asked this now. Who asked this? Are you there? I'm thinking the combined gas law. Things are changing. So, write it again. Okay, it appears that the temperature is not changing. So forget that. It appears that the volume doesn't change. Sealed container, yeah. Is that all right? Okay. So let's see. The initial pressure is 600 kPa. Cool. The final pressure is what we want to know. That's what we want to know. The initial moles, how many? What's the initial amount of moles? Anyone? 3.5. Not 3, 4. How do you know that? That's right. 3 and 1. I started with the sum of, well, the sum of all those. Adds up to 4. That's 4. What's the final moles? Sum of all these, 4. So in your head, I start with 4 here, and with 4 in your head, the final pressure is 600. The moles don't change, so the pressure can't change. Is that all right? Cool, that was easier than I thought. Nice. Could have done that in your head. Okay, next. Yes, whoever of you two wants to go. Page 74. Okay, I'm on page 74, exam to fall 2014, right? And I'm on number 17. Which part of 17? This is page 74. We're looking on the uncertainty principle. Okay. This is, again, fall 2004, number 17, page 74. Oh, 2014. Sorry. Nice. 2014. Okay. Let's see. This is the uncertainty principle of an electron whose velocity, so the velocity is 5% the speed of light, c. Okay, so the velocity is 5% of c. Let's see. I want to know the uncertainty and the position, so I want to know x. Okay? And let's see if there's anything else I know. That's it. So, the formula as given would look like this. Well, all right. M delta U greater than or equal to h over 4 pi. I told you, hey, rewrite this in a way that makes sense. H M U percent equals h over 4 pi. I want to solve for x, so let's do that. X is h 4 pi m u percent. Okay, so now we plug, it's basically plug and chug. Oh, you're right there, yeah. So 6.626 times 10 to the minus 34 joule seconds. 4 pi, where do I get the m? It's the mass of an electron. I find that on the back of the exam. Yeah, it turns out to be 9.109 times 10 to the minus 31 kilograms. Okay, I'm kind of running around the room here. What's U? Yeah, so 5% of C is the U and the percentage together. Is that okay? So typically in this problem you'll see a percentage given. It'll usually say like an accuracy or precision or known to something like that. So these two go together. So the 0.05 and then I'll just write C, write the speed of light in there. Is that okay? Plug and chug. Okay. Next, there's something up here. Yes, in pink. You look like you were looking at your wrist there. Yeah. Oh, okay. But there's no watch. Okay, awesome. I like that. What time is it? Time to go. Okay, 61 number 9. Are you talking about this one right here? No, we got it. Okay, this is winter 2016, number 9, page 61. Okay, a gaseous hydrocarbon, 0.231 grams, has a volume, so this is a mass. The volume is 102 milliliters. The temperature is 23 degrees C. It says the pressure is 749 millimeters of mercury. I'm just writing down everything I have here. I want to know the formula. Meaning, is this CH4, C2H6, whatever, and there's a lot of choices in the answer. Okay, notice first, things aren't changing. So there's no pressure change like there was in the previous ones, or temperature change. It's constant. So I'm thinking ideal gas law. And there's a variant of the ideal gas law that uses mass and uses the formula. So that kind of fits nicely. We got P, V equals N, R, T. Maybe I'll write it this way. The molar mass is mass over moles. Or let's solve for N, because that's what's in my formula. That's mass over molar mass. So PV is mass over molar mass, RT. Okay, really, to get the formula, I'm going to get that through the molar mass. So it's really, when it says what's the molecular formula, solve for the molar mass, or capital M. Okay, now you plug and chug. 0.231 grams. R is 0.08206 liters atmospheres per mole Kelvin. Temperature, 23 plus 273. P, oh, I guess I'll ask you, can I put millimeters of mercury in here? No, I do have to change that. To what unit? Yeah, ATM. So on the back of the test, it gives you this conversion, 1 ATM for 760 millimeters of mercury. And then the volume is 102 milliliters. Is that okay? Can I put milliliters? No, I have to put liters. I'll just do the conversion. It's 0.102. You got to divide by 1,000. Go from milliliters to liter. Whatever that is, then you just find that number, add all these up to see which one adds up to the same molar mass. Is that okay? Okay, good. Who's next? Yes, 1, and I'll go 2 back there, and then 3. And then you're going to cut the cord. Okay, yes. Wait, who had the first? Wait, that was you? I thought it was back there somewhere. No, it's... Oh, you were on behalf of someone else. That's really funny. Okay, yes. Fall 15, number, page 64. You mean 65? I don't know what number yet. This one? Okay, it's number 8, page 65, fall 2015. This says 8.21 liters C3H8 that burn, meaning combustion. So the word burn means combustion. Burn, explosion, combust, anything like that. We'll have to balance this maybe later. Okay, so all the gas volumes are measured at the same temperature and pressure. Okay, cool. Wait, what does it want to know? It wants to know the volume. How many liters of oxygen are consumed? All right, we need to balance this. Let's do that. Oh, you already got it for me. 3, I don't even have to think. 3 and 4, I love it. Okay, let's assume that's right. I like it. Okay, now, I know that this is 8.21 liters. Okay, so let's use the law of combined volume, see if that works out. So I've got liters of the C3H8. And there's 3 liters of oxygen for every 1 liter of C3H8. Oh, I multiply that number by 3. Is that a possibility? Oh, I didn't balance it. What? Someone was lying to me? You failed me. You definitely, man. Okay. What do I put here? You want 5. Okay, that's all right. Next time, just get it right on the test. That's all I want, okay? So put a 5. So 5 times, is that one of the answers? B, maybe? Okay. You're good? Okay, who's number 2? Yes. 2014, number 17. Wait, what page?
58 in my reader.
Oh, that's not helpful. Okay, wait, fall. Wait, I'm confused again. Fall?
2014.
2014, number 17?
Yeah.
Okay, now I'm with it. That's page 74, the current one?
Yeah,
What part?
3.
3. The liquid nitrogen?
Yeah.
Okay, so this is page 74 for everybody, or fall 2014. Okay. Liquid nitrogen is poured on balloon, causes contract. What approximate? Oh, so things are changing here. We're going from 22 degrees C, it says, to negative 120 degrees C. So we see a change in potassium gases, so again, combined gas law. So R is PV1, same formula you've seen me write a couple times now, P2V2 over N2T2. The temperature definitely changes. Let's see. The volume changes. The pressure, let's see. Doesn't say anything about the pressure, so I'll assume that stays constant. Let's see what else we got. The moles, it doesn't say that anything escapes, so I'll assume the same number of moles of gas stay on the inside of the container. Is that okay? So once the volume fraction, let's get this right here. What fraction of the original volume will the balloon shrink? So that would be, of the original, it looks like V1 over V2, because V1 is the original. Is that okay? I think. Let's see, well, let's calculate and see what we get. T1 over T2. So T1, the initial is 22 plus 273, and the final is minus 120 plus 273. Let me make sure we got the volume fraction right. Okay. What approximate fraction of the original volume? So this is initial over final. I guess I'll ask everybody, do you think this would be the correct answer, or the inverse of this would be the correct answer? Okay, if it's inverse, why inverse? Because of the time. Wait, say it again. This is not Graham's law, so you wouldn't think, don't confuse this with Graham's law. Yeah. So I'll read it again. What the approximate fraction of the original volume? So is the balloon shrinking or not when it cools down?
Yes.
Yeah, so the fraction of the original, let's say it's like 50% the original volume, right? You'd expect the number to be smaller than 1. So I'm looking for, if that's you up there, I forgot. Did you ask? Yeah. I'm expecting probably the number to be smaller than 1. So let's see. We are 3. Yeah, it gets A, so 0.52. So I just arranged the fraction to get less than 1. Is that okay? We're thinking about it? Okay, you think while I go over to the last person. Who was the last person?
Wait, so it's the other way, right?
Yeah, it's the other way, the opposite of this. That's right. Last person was down here somewhere? Yes? Winter 16, number. Okay, last one, then we'll close up shop. This one right here. Is that right? Oh, where'd you go? Is that this one? Okay. Winter 2016. This is page 661 for this quarter's manual. 12, right? Is it 12? Okay. Oxygen gas is collected above. Oh, yeah, I'm glad we did this one actually. You see the word above? That's a synonym for over. So above or over, same deal, same prepositional definition. Or the semantic range, I guess, is similar. Okay, so it's collected, the temperature is 11.9 degrees C. The volume is 24.6 milliliters. If the vapor pressure of dichloromethane, vapor pressure of, that's a long, I'll just put D for dichloromethane, okay? The vapor pressure of D at 11.9 is equal to 247.5 millimeters of mercury. And the barometric pressure, P total, is equal to 695 millimeters of mercury. How many molecules of O2 gas are collected? So, we want to know the molecules of O2. Okay, so this follows our over water, but this one's not over water, it's over capital D, the dichloromethane. Same process though, so let me set it up, and hopefully that'll get you started. Okay, so the setup would be P total, just like we did before when I was talking about the Dalton's law. That's the partial pressure of the gas, plus the partial pressure. This was water before, but now it's the dichloromethane. So the one, generally this is collected over or above water, but this one happens to be over or above dichloromethane. So this, let's get a different color here. This is the one you're looking to solve for. P total is right there. And the partial pressure of what says the vapor pressure of D, that's the partial pressure of the D. So that's, both of these numbers are given. Is that okay? You're going to solve for the partial pressure of the gas, and then you're going to use the second formula you saw me write down earlier. The moles of the gas is the partial pressure of the gas times the volume over RT. Let's see what we got. We got the partial pressure of gas. That's from right here. Okay, solve for that. Put it in there. The volume is 24.6 milliliters. Is that an okay unit? No, I need it in liters, so it'd be 0.0246 liters. R is 0.08206, and temperature is 11.9 plus 273. Change to Kelvin. Okay, do I want the moles of gas? No, I really want the number of molecules of O2. So how do I go? Yeah! Moles of gas. If I have the moles, then I'm going to go 6.022 times 10 to the 23 molecules per mole. All right? So that's a setup. Try that, see if that works, and if it doesn't, come see me.